So far, we've fitted the model, which is truly great. Unfortunately, we've got a problem. We'll need a way to assess which independent variables contribute to predicting borrower default and which don't. In our final model, ideally, we are going to keep only those independent variables that actually contribute to explaining the good-bad dependent variable. For most statistical methods, the accepted approach is to check the statistical significance of the coefficients of each dummy variable. One of the most common ways to achieve that is to look at p-values. There are some built-in methods for calculating p-values in sklearn, but they are univariate, meaning they take into account the impact of each feature on the outcome as if there weren't any other features. In a regression model, the impact of all the features on the outcome is collective rather than independent. Therefore, the insights we get from such methods will be flawed. Unfortunately, the logistic regression model does not have a built-in way to calculate these multivariate p-values. In fact, obtaining the multivariate p-values from an sklearn is always tricky. One of the cleanest ways to achieve that is to alter the fit method from the logistic regression module itself. Let's create a new class called logistic regression with p-values. Here is the code for this new class that we've called logistic regression with p-values. We won't go into details about the calculations the code performs, as they are rather advanced linear algebraic operations. Let's only briefly go through the different segments. An instance of this class initializes by inheriting everything from the original logistic regression class. Next, we define a fit function which overrides the original fit available in the original class. In it, we compute the multivariate p-values we need in this segment of the code. At the end, the p-values are stored in a variable called p-values. By design, obtaining these p-values will be very similar to the way we extracted the intercept and coefficients earlier. Alright, now let's see that in action. I'll overwrite the existing reg variable as an instance of the newly created class logistic regression with p-values. Once we've done that, we can run the fit method just like we did before. We can also use the same code to overwrite the summary table and display it. And here it is, exactly the same as before. However, we have a new piece of information we can add to this data frame, the p-values. Let's add the p-values in a new column next to the coefficients. To make the code more semantic, we can extract the p-values in a variable called p_values, which equals reg.p_values. This piece of code will allow us to access the p-values from the newly created class. Now, because of the way the logistic regression with p-values class is written, what we get here are only the p-values of the coefficients of the independent variables. We don't have a p-value for the intercept. In order to match the p-values to the coefficients as columns in the summary table, we can add something on the first row, the position which corresponds to the intercept in the current summary table. We can simply add an NaN value. So let's make the existing p-values list equal to an NaN value and an NP array of the existing p-values. We'll use NP_append to stick them together. Now we can create an additional column in the existing summary table called p_values equal to the p-values array. Okay, as we display the summary table now, we can see that there is indeed a third column with the p-values. Let's analyze it then. There are 104 dummy variables in our model, and here there are coefficients and their p-values. I will paste them in a spreadsheet to make them easier to read. Okay, we've got the coefficients and the corresponding p-values. Now we can select independent variables based on them by only retaining the variables with coefficients that are statistically significant. It's good to remember that each original independent variable is represented by several dummy variables. So if the coefficients for these variables are all statistically significant, we surely must retain all of them. Then, if none of them are statistically significant, we should remove all of them. But what happens if the coefficients for some of the dummy variables are statistically significant and others are not? Technically, it surely makes sense to remove the non-statistically significant ones. But if we do that, there will be few variables in the model representing a part or parts of the original independent variable, while there won't be anything representing the rest. Conceptually, that doesn't make much sense, right? Hence, if one or few of the dummy variables representing one original independent variable are statistically significant, it would be best to retain all dummy variables that represent that original independent variable in the final model. Let's apply this approach to the first logistic regression model we estimated. Conventionally, if a p-value is lower than 0.05, we conclude that the coefficient of a variable is statistically significant. Let's start in order. The coefficients for all dummy variables that represent the grade variable are statistically significant. Thus, we keep these dummy variables. The coefficients for all dummy variables that represent the home ownership variable are also statistically significant, so we keep these dummy variables as well. Next come the dummy variables that represent the address state variable. All but the first are statistically significant. Once again, we keep all of them. What follows is the dummy variables that represent the verification status. Only one of the two coefficients is statistically significant, but that's enough to preserve both variables for the final model. If we keep examining the subsequent dummy variables in a similar vein, we'll conclude that we should keep all dummy variables up to those that represent delinquency in the last 2 years. These two variables are not statistically significant according to the widely accepted criteria of 1%, 5%, or even 10% significance level. So let's remove all of them from the final model. Then we have open accounts. Only one dummy variable is statistically significant, yet we keep all of them. None of the coefficients for the dummy variables that represent public records and total accounts are statistically significant, so we remove these variables altogether. There is only one dummy variable for accounts now delinquent. The coefficient is statistically significant, so we keep the variable. From the dummy variables representing the original variable total revolving high limit, the coefficient of one dummy variable is statistically significant at 5% level, of another one at 10% level, and of a third one at less than 0.1% level. We could keep all the dummy variables here, but note that the coefficient of only one category is statistically significant, really. So, we can and will opt for removing all dummy variables that represent the total revolving high limit independent variable here. Using the same approach, we decide to keep all other dummy variables. To sum up, for the final model, we removed the dummy variables representing the following original variables: delinquency in the last 2 years, open accounts, public records, total revolving high limit, total accounts. We keep all the rest. All right. How do we do that in terms of coding? Well, let's overwrite the list with the names of the independent dummy variables, which we called inputs trained with reference categories, again, taking only the dummy variables we need from the loan data inputs train data frame. Remember that in this data frame, we took all the dummy variables, including the ones that will later serve as reference categories. Now, by analogy, let's overwrite the list that contains the names of the reference category dummy variables to contain only the reference categories of the dummy variable sets we want to keep for the final model. We can then copy the code from above to override the inputs train data frame, making it equal to the inputs train with reference categories data frame, with the reference categories dropped. Now the inputs train data frame will contain only the new set of dummy variables we are going to use in the new model. Let reg2 be another object of class logistic regression with p-values that we defined. Then, just like we fit the reg object of the same class, let's fit reg2 with arguments the data frame with independent variables inputs train and the data frame with dependent variables loan data targets train. Then we can use the same code from above, storing the names of the independent variables in feature name from the new inputs train data frame. Finally, We can also use the code from above to create a similar summary table. Just as before, the summary table won't contain the p-values, so we can use the same code to append them, this time from the reg2 object. Alright, we now have the final PD model. After we selected only the highly statistically significant sets of dummy variables, the final model contains 84 independent dummy variables. Once more, I'll paste it in a spreadsheet in order to be able to read more easily. And here they are, the coefficients for 84 dummy variables that represent 17 original independent variables. In the next lecture, we are going to interpret these coefficients. Thanks for watching.